theme is current status of ARPIP development. Of course, this will be sort of emphasizing a bit the developments we had performed within Discover, with a certain element along with what literature reviews tell us, along with other ARPIP concepts in ours. The presentation will be on ARPIP in itself, including the intake principle and its operation and designs, and then the development test of our advanced RF Helicon plasma thruster. But behind this, we know that the work that we did ourselves was significantly supported within Discover. We had a lucky aspect with regards to the work we did, because we could benefit from a funding structure along with a scholarship for Francesco Romano before, which paved the way and prepared the ground very well for the entire works within Discover. So in principle, we can say that along with the ARPIP development, we spent even some 2.5 years or 1.5 to 2.5 years more than the entire period of Discover is. Behind this, there are a certain level of research questions. For example, what are the main driving parameters and their ranges for designing an ARPIP-based mission? Or what is the principle of operation of an ARPIP intake, and how can the system efficiency or the efficiency be maximized? How to design an efficient electrode-less plasma thruster that operates on atmospheric propellant? How can the more or less complex plasma physics-driven phenomena be approved, which means how can we prove that our advanced Helicon is a Helicon? And what impact can application, for example, Earth observation or telecommunication, launcher, and ARPIP in general have, referring to the platform design, which means the design of the satellite that shall benefit from the ARPIP system? Of course, we will not be answering all of those questions within this talk, but I will give certain elements that path the way that one should go in order to assess these questions. On the other hand, some of those questions will be answered more or less completely during this talk. The point of departure is that we have the situation that a platform that operates in the very low Earth orbit suffers from the drag produced by the residual atmosphere. And the idea behind ARPIP is to come up with a system, propelled system, a thruster system that compensates this drag on the one hand, which is a state of the art if you consider the standard established EP systems, but then to go a step further and say we use a system that is enabled to collect in flight direction the thermospheric masses or particles as mass that is then used as a propellant for the thruster. In other words, we have the system design that benefits from what we call an intake or mass collector in combination with an adequate thruster. And the adequacy, of course, of the thruster is a more or less longer discussion, because we learned in the past few years that ARPIP developments are sort of twofold. One community tries to modify or make use of existing or established or well-established EP systems by modifying them in a way that they can cope with the operational requirements in terms of, for example, propellant, in a way that they compensate then the drag, which is, for example, some people that work with whole iron thrusters. And the other community is saying, okay, let's do something from the new that can elaborate advantageous scenario in a way that the newly developed thruster can cope with certain aspects that are accompanying its operation in VLEO in combination with an intake that provides oxygen and nitrogen species to the thruster as propellant. And this is a bit different because it tries to start a bit more from the scratch, but to build up a beneficial scenario by enabling the thruster to do so from the beginning. Now, when we look at VLEO scenarios, we have, of course, to assess what happens here. And the diagram shows the species-wise composition of the thermospheric zone of altitude starting from 100 kilometers up to 450 kilometers. We can say or assess that starting from altitudes around 450 or let's say 400 kilometers, the drag is that significant that it plays a role for the lifetime or the lifetime aspect of the platform in view. For example, the ISS has to run through regular maneuvers that lift the orbit, making use of remaining propellant masses in the Progress transporters from the Russian colleagues. But when you look at the diagram, you see that we have to encounter or consider mostly atomic oxygen and nitrogen, which puts a certain level or an agenda on the assessment on the way on how atomic oxygen can impact such a mission, and in particular also the thruster, meaning that atomic oxygen is chemically aggressive, produces erosion with or without arc in an propulsion system, and leads to the fact that a certain level of characterization and qualification of the thruster has to consider that the atomic oxygen can be difficult. The advantages of VLEO in turn are quite evident. We can benefit from less complex optics. We can reduce the antenna sizes and the needed power for this purpose. We can rather use standard components because we suffer from a reduced radiation. We have a reduced collision risk. And we have a self-end-of-life satellite disposal because the natural decay of the orbit is within temporal domains that are in the orders of weeks or months, or say less than a year. And this is quite important because it ad hoc and automatically fulfills the code of conduct. All in this motivates VLEO missions and, of course, the attempt to provide those VLEO missions with significant lifetimes by making use of an RBEP system. RBEP in literature is quite manifold. We have developments in Japan, we have developments in Italy. I guess the Italian development with CITAL is one of the strongest because it has undergone a certain level of continuity throughout the entire phase of the past 5 to 10 years, which is quite important. In this way, it's about comparable to the development period that we had within Discover. Most of them employ thruster systems that are standard, in other words, that are already existing and well qualified for other purposes than RBEP, like ion thrusters or whole ion thrusters, but they suffer from these aspects mentioned before, namely erosion, the bad compatibility in between the thruster and the propellant it receives in terms of oxygen and nitrogen, for which it hadn't been designed, and the resulting reduced thrust efficiencies and maybe the reduced lifetime, which may justify the statement that such developments take the risk that the lifetime issue is moved into the RBEP system. Sounds a bit polemic, but I guess you understand what I mean. So at the end, this brings us to other developments. And the point of departure for our development was to look at features that the thruster must have in order to overcome these several burdens, like the erosion by the atomic oxygen, the more or less reduced efficiency, systematic issues, and so forth. And you see the red text. We decided upon an electrodeless thruster, an RF thruster, for several reasons. One reason is it produces a quasi-neutral plasma jet, so we don't need a neutralizer. And the neutralizers are another bottleneck for the whole ion thrusters and ion thrusters because it's quite difficult to run a neutralizer with the thermospheric species. It's in principle the same problem that you have with the thruster in itself. On top of this, this is a systematic simplification because the neutralizer represents a significant subsystem that we just don't need for the electrodeless thrusters. In addition to this, as a result from the fact to have no electrodes, we have a more or less significantly increased flexibility towards the propellant composition and likely even with regards to the propellant density. For example, density is an issue for some of the other thrusters. When you get too high in altitude, they suffer from a certain threshold values in needed minimum density to be operable. And we see this problem as well for our thrusters, but we consider that this problem comes later, so at higher altitudes. Okay, no lifetime problems referring to the electrodes, I already mentioned it. And we have a significant potential for comparably higher thrust efficiencies. For example, if you compare with non-optimized air-driven whole ion thrusters, we can say that those thrusters are at 15%, and we expect for our thruster, at least based on the literature database we have, values at 18-20%. And due to the fact that we decided upon a very specific electrodeless thruster, we even hope to get higher efficiencies. But why that is, I will explain later on. I would like to skip those slides. Those slides here show works within electrodeless thrusters, also in applications beyond RBEP, just to mirror that this theme is an upcoming theme in the world and that there is a certain level of database, also literature-based, from which we could benefit when we started working in that field. So there's in particular Tohoku University with quite high thrust efficiencies in an order of 18%. Then there's the ANU, of course, with Rob Boswell and Christine Charles. Then there's Carlos III Madrid in Spain, and T4I, of course, with whom we now collaborate in an ESA project for fostering the RBEP system, making use of their PPU technologies that they had already qualified. Maryland in the United States and Washington, which employs a high power helicon, and that's it. Now, as I have said, we have a combination of subsystems. We have the thruster and we have an intake. And the intake is a quite not complex, but complicated thing in terms of mass collection and the provision of the propellant to the thruster. And this was a quite difficult task because we started there from the scratch and had to make use of our in-house DSMC and particle and cell code system that is called PICLAS, and came to two designs. One design which assumes diffusively reflecting materials as surface material, and the second design group that assumes specularly reflecting materials as surface materials, which turns the system into rather a quasi-optical system where you rather come up with mirror-type designs, parabolic structure that focus the particles to a focal point, which has to be more or less very close to the entrance of the thruster in order to achieve very high collection efficiencies. So this parabolic structure shown here signifies the design for a specularly reflecting system, and this system with the small ducts is the resulting design for diffusively reflecting material surfaces of the intake, where you make use of the honeycomb type structure or the small duct structure in order to have an increased probability for particles that enter the system, but a comparably reduced probability for the particles that are in the system, in the reservoir, to be able to come out, which is preemptively tried to be shown with the blue arrows. We came up with these two systems, and in principle, we then have three systems because the very start was the EFD intake, and later on we had what we call the diffuse intake and the specular intake. And with diffuse intake beyond the year 2020, we achieved, numerically at least, collection efficiencies in an order of 46%. And with the specular reflecting intake materials and the parabolic structure, which you see on the right side, we achieved numerical values of 94%. We have, of course, to consider this with care because these are designs that are based on numerical simulations. However, we verified our approach by comparing our results with the results of others. For example, we quite successfully could rebuild the efficiencies and the compression ratios that were also simulated by JAXA for their own intake design. So we did a certain, let's say, approach in verifying our tool, which gives or provides these results with a certain level of confidence. Whatever it means, of course, with regards to the potential degeneration of the surfaces. For example, nobody knows how long a supposed specularly reflecting surface remains specularly reflecting when it is in orbit. And we assess this in our publications in terms of looking at a certain level of decay and what it means to the efficiency. And we still see that we still have, independently from this, quite high efficiencies, at least higher than the ones by the diffuse intake, but we do not know the temporal behavior because for this, we do not have an adequate database material-wise. This diagram shows a comparison of the gathered mass flow rates for the different intakes. It's a bit difficult to compare because we use different areas for whatever reason, so intake areas. But anyway, you see the order of magnitudes and you see that the specular intake seems to gather the highest mass flow rates. This is very important because a higher mass flow rate decreases the requirement that we have to fulfill with the thruster on level of the ISP, on level of the effective exhaust velocity. So it's a bit important to keep this in eye and to not forget this. The simulations that we see here on the right side for the diffuse intake, on the left side for the specular intake, by the way, this arrow with the inflow is of course wrong, shows the results with the compression ratios, so the differently colored scaled colors where you can guess preemptively here in the specular system a focal point, which is really the case. There's a certain level of focal point, which has to be, according to our simulations, quite close to the entrance of the thruster in order to achieve high efficiencies. And the specular intake is much less sensitive with regards to misalignment. When the intake is misaligned towards the flow inverted comma, it suffers less as compared to the diffuse intake. So this is another important result. With the system analysis, we did a certain level of loop link, making use of our own tools, but we also compared these tools with the tools with the University of Manchester quite successfully, at least on the level that we can say there's a certain level of verification. We employed the NRL MSCC 00 model for the atmosphere and built a loop between the mission envelope and the atmospheric properties, the performance of the RBEP system, and then derive from this a certain level of system analysis results. This was quite important to us because it also provided us with mass flow rates, which we then used later on to test our thruster. So we copied those mass flow rates into the tests, the experiments. Those equations, which you see here, you could consider as a certain level of surrogate model to assess this. You can derive an equation for the drag, you can derive an equation for the jet power of the thruster. You can say you equalize the thrust with the drag, which is not necessarily needed. You can, of course, have equilibrium, but you can also have missions where you have, on average, the equilibrium, but you have cost phases where, for example, the thrust is lower, or where you do not have thrust at all, for example, for the reason of being in a shadow phase or whatsoever. Let's remain with the T equals D. Then you can derive an equation for the power that you need. And this power depends on 3 parameter domains. One is the atmospheric properties and the mission envelope, which is circled in violet. The second is the spacecraft properties, which is circled in green. And the third is the RBEP performance properties, which is circled in blue. And you can easily see that eta C, which is the collection efficiency of the intake, and eta T, which is the thrust efficiency of the thruster, are bottlenecks. Or positively speaking, you have to do the maximum to achieve that you have high values in eta C and in eta T. And respectively, also you have to see it in the entire scenario. A similar approach results for the specific impulse, but I don't show this. For verification purposes, we then applied our mission analysis to a Cocher-like satellite, which built a certain level of confidence that such a mission would be doable. So we used, for example, for the thrust efficiency 0.2, and for the collection efficiency, we used the values from the diffuse intakes and the specularly reflecting intakes, the maximum values. Then we looked at the altitude and the needed power and compared the power to the available power of Cocher. So we found a corridor where we can say this is operable in a certain way. Then we started with very first experiments, and those experiments were performed with a system which is not yet the system that we developed later on. We did that to come up or to identify the needed measurement techniques to train the guy, which was Francesco Romano, and to may assess certain elements of which we were aware that they shall apply to the later on built Helicon thruster, the IPT. This element is, for example, the static magnetic field that is typically superposed. So there was a coil, and we wanted to look at the effects that we can observe. And this is shown on the next slide here. And what you see here is an operational history in a quite preemptive way. And you see several features. So we superposed this magnetic field by making use of a self-designed DC coil. And you see what happens. For example, here, when you see the mouse at around 3,700 seconds, you see that the magnetic field enabled ignition. In other words, without the magnetic field, we haven't had ignition. With magnetic field, we got ignition. And we saw that with the magnetic field, the operation became much more stable, which you see at the arrow where it says 6.8 millitesla. And with the increase to 27.1 millitesla, we saw that the power tripled. And this is a very strong element that tells us that, on the one hand, it's advantageous. On the other hand, it implies that this either must be a significant inductivity change and or a hint to Helicon mode. This is not a proof. This is just an element. So a certain level of element that build a certain level of confidence for us to continue our development. What does it mean? It means that we replaced the thruster here, which is here presented with the solenoid surrounding the coil, and the coil as well as a solenoid, then started to turn into a new design with new antenna technique and certain elements that are new due to the antenna technique. And this was in principle a birdcage antenna, to which I come later on. And before we did it, we looked at analysis, making use of standard tools, I would have almost said, like Helic and Adamant. Adamant is the coach from Padua with whom we started collaborating. And we started to use this for simulations along with matching, but also for simulations along with resonance. So I do not say more at this stage. I'm just saying we use this for simulation and assess a certain level of design. With the birdcage antenna, which I don't show in detail because this is more or less the core of the patent we had submitted, we have an antenna which is not looking like a solenoid, but a set of legs that surrounds the plasma container. In our case, we used 8 legs. The physics tells us that depending on the number of legs, there's a certain number of potential resonance that can evolve. And one of the resonances allows to employ a drift velocity to ions and electrons along the same direction due to a linear polarization of both electric and magnetic field of the antenna. So the static field doesn't play a role for this purpose. For other purposes, yes, but not for this purpose. So we have E1 and B1, and they are perpendicular to each other and allow for a drift velocity, an MHD effect that accelerates the charged particles, which you can also see here with the velocity vector. You see here the velocity vector, where it says that the Z component is about proportional to E1 times B1. The Y component is proportional to E1 times B0. B0 is the static field, and E1 does oscillate. So it means that there's an effective value which you can consider as about 0. This is the thruster. I only show the outer mode line. I do not show the antenna design. This is the new thruster, a helicon-based thruster with the original and novel aspect of making use of a bird cage antenna. This is the new thing in this thruster. And here on the right side, you see the solenoid surrounding it, and we consider a power lower or equal than 1 kilowatt, an 8-legs bird cage with an operating frequency at 40.68 megahertz. And we use the XF-DTT software to extract the required capacitance. This is the thruster as it is mounted. And the simulations shown here show the S11 parameter in decibel over the frequency. And you see here on this side, you see a resonance, which is almost in correspondence with our 40.68 megahertz. On the right side, you see the Z against the frequency. All these simulations are performed without plasma. So it's vacuum solutions. So there must be a discrepancy, of course. And we verified the correctly chosen resonance by assessing E1 and B1. And you can see here that E and B oscillate in a constructive manner in the sectional area of the tube, leading to the E cross B drift velocity for the charged particles. And this is the right point. So we hit the right and correct resonance. We, of course, measured it. And of course, there's a difference between measured and simulation. But this is a difference before matching and before adapting. And the difference is, lucky enough, not too high, as you see in the table. So the relative differences in frequency are below 4%. In amplitude, they are significantly higher. Then we tuned the device, and the tuning led us to this result from the network analyzer, showing up with an impedance which is at almost 50 ohm with an almost zero complex component. So very well adapted, very well matched. This matching is important because it minimizes also the reflected power. Hence, it maximizes the coupling efficiency, but not yet the thrust efficiency. Only the coupling efficiency. So what we couple from the electromagnetic waves into the plasma is supposedly high, but the thrust efficiency is still unknown because we haven't measured it. This is the first ignition in argon. It's images, photographs. As always, when you see a plasma, quite impressive. And this might be more important. This is argon, nitrogen, and oxygen with respectively underlying mass flow rates or flow rates, showing that the thruster can be operated with pure oxygen as well as nitrogen, as well as mixtures. Then we played a bit with the parameters, which might be not so important at this place. And the limits that we have so far are at 60 watt as lower end and 300 watt at the upper end. We know that the power unit can also employ values in an order of 1 kilowatt, but we haven't done it yet. The next steps are looking at the helicon mode. We have the helicon wave with the polarization. And when we can visualize the dynamic behavior of the helicon waves by measuring it, then we have the approval that we have a real helical mode. And this is in preparation, making use of a B-dot probe, which is newly designed. It's a 3-axis B-dot probe, fully designed, fully built, has already undergone certain level of calibration activities. This is how it looks like, more in detail. And this is how it looks like when it is then mounted to the thruster. This is one part of the calibration activity, showing the different components of the magnetic field that we employed to the probe for the calibration activities. The second element which is missing is the thrust measuring. We want to have the thrust measurements because this is the prerequisite to be able to determine thrust efficiency and ISP. Also the characterization of the plume. We make use of a baffle plate with a torsional thrust balance with a certain sensor equipment standing on the slides. A trade analysis showed that we opt for a torsional pendulum at the very low end of the thrust value measurements. We expect thrust values lower equal than 1 millinewton. So we are compared with Takahashi at the lower end of the thrust values. And this is the final design. And we are currently procuring the parts and pieces and building up the balance. This is how it looks like when it is mounted. Calibration is also foreseen with an electrostatic force element that we use to calibrate the forces that the torsional balance will measure. And this brings me to one of my last items, namely the platform considerations. The work has continued within an ESA project, and the boundary conditions are an SSO orbit at altitudes between 150 and 250 kilometers with an optical payload and a telecom payload that was identified in terms of requirements by ESA, and certain constraints on level of the analysis were that the outer spacecraft surfaces are made of diffusely reflecting material, and we have a length element of the spacecraft that is linked to the launcher payload bay, which is at approximately 4 meters. We used for our system analysis a thruster efficiency of 0.2 as before, and the two relevant intake efficiencies of 46 and 94% respectively. We aimed at a realistic maximum ISP of 2000 seconds and the maximum specular intake diameter to maintain a length of 3 meters of 0.5 meters. This is quite huge. This led, and I skipped the left one, this led in principle to the flat body design. So we have a flat body design with several intakes and thrusters. This is due to the fact that the ISP requirement of the flat body design is significantly lower. The CD is slightly higher, so the drag coefficient is slightly higher, but we benefit from the significantly higher eta C, the mass collection efficiency of the used specular reflecting intake designs, the parabolic structures, while the slender body was assessed for the diffuse systems. The required RBIP power of the flat body is significantly lower as well. So we need less power, meaning that the penalty of the slightly higher CD is compensated again by the high efficiency of the mass collectors, the intake. This brings me to the conclusions. What have we done? We have done literature review in assessing both the RBIP R&D activities in the world as well as the R&D activities in the world of electrodeless RF thrusters. We investigated the main mission parameters, the RBIP efficiency, the variability of the atmospheric properties in terms of composition and density. The RBIP intakes were investigated. We did preemptive experiments making use of the inductive plasma source IPG6S, hopefully with a certain beneficial aspect along with the use of the DC magnetic field that tripled the power and enabled ignitions at points where ignitions weren't possible before. So maybe we even have assessed an helical mode, but we cannot prove it yet. The system emission analysis was to assess the feasibility of the corresponding sensitivity scenarios and provided a database for the operational parameters for the designed intakes as well as the IPT, which we tested under the given mass flow rates and mass flow rate range we had identified via our system and emission analysis. We designed and built a new plasma thruster based on a cylindrical birdcage antenna that is derived from Medison technology. We had at the lower end power requirement of 60 watt with a tuned and matched load at shielded. It works contactless, so we have a maximum propellant flexibility with regards to density and composition. We are quasi-neutral, so no neutralizer is needed. We hopefully can benefit from the drift because the drift is the new element in the regime of helicons. We did experimentally a preemptive proof of concept by testing the device with nitrogen and oxygen and comparable mass flow rates. We designed and integrated a magnetic inductor 3-axis BDOT probe, and we are currently building up an adequate thrust balance. We assessed advanced and alternative RBIP mission scenarios, which I haven't shown here. Beyond this cover, we looked into platform design and the potential thruster design, which is at a comparably lower size and power adequate for this platform design. Outlook. For this cover, we still need to do the BDOT probe calibration and measurement, and we need to perform the thrust and ISP measurement. This is definitely needed. Beyond this cover, we have certain elements in plan to further characterize the device with Longmire probes and Faraday probes and an RPA, but there are still works ongoing to compensate them for the RF field. The design of the thruster for vacuum operation is already in preparation, so the new thruster will be able to be operated in vacuum environment, rather than just being flanged at the outside of the tank. So this concludes my talk. Thanks for listening.